Okay, there we go. So we're on lecture 30 today, and I've got the links posted. I'll repost them again in just a minute. I expect we'll have a couple more members. So rather than doing that a bunch of times, I'll just wait a minute and then post them before or once we get to the first exercise, maybe. All right, so we're going to talk about really actually the broader subject here is error handling, not just exceptions. So we'll talk a little bit about what that is. Basically, we'll do a really quick review. I'm not going to go into all the stuff from the other day, but just once again to keep it foremost in your memory. And then we'll talk about our today topic, which is error handling, which covers asserts and just exits and error output in general, and then also exception handling, which is a little more involved, but one I think you guys can all understand and use someday. So just kind of actually an overview of what we'll cover is, actually, I think I might have left out my review slides. Well, lucky for you guys today, you won't have to go through review, so we'll just jump right into it. So types of errors, right? Of course, syntax errors we are all very familiar with, and we see increasingly integrated development environments or IDEs that pick that stuff up and give us hints even before we hit the compile button that let us know what's going on. And if you've got a good one of those, you know it because you get really used to it. Now, of course, there's also link errors, right? Stuff that happens kind of between the compiling part and the runtime part where things in the compile units or the translation units are all fine, but we put things together, we can't resolve stuff. So we've seen some of that happen when we work with multiple files like multiple .h's and CPPs. That's kind of stuff we've learned a little bit how to work through. And of course, runtime stuff that happens where there's dynamic allocation, pointers are null, maybe we divide by 0, do something like that that's going to cause a problem. And then semantic errors are the ones that just, they're just the bad data, right? It all worked, but it really wasn't what we intended. We had maybe a logic error in how we were maybe doing something, or an infinite loop, or recursion failure. We didn't have our base case set up or something like that. So those are kind of the different categories. And so there's some tools that we have that allow us to work with that stuff more formally. We're going to talk about today. CERR is just basically an output option for redirecting your output to a log file. It's kind of nice to know that exists. Emergency kind of pull the ripcord. Exit we've seen a little bit of. We'll talk about asserts. And then this exception system that has gotten increasingly more sophisticated in recent releases of C++. So let's take a look, just talk about the easy stuff first, which is exit and CERR, to make sure you guys understand that. So exit, as we've seen and many of you have used before, is a controlled termination with some kind of basic unsigned status. So if we have some function and we decide that something really fundamentally bad happens, we can exit, and we can additionally provide some status code that can be interpreted maybe by an operating system or by some other program that maybe is monitoring our exit status, something that maybe we've run. So that's a pretty straightforward thing we can do. There's a few things that it's useful to know about that exit. It's going to try to clean up a few things, especially since C++11. File pointers, close down some threads, that kind of stuff. But not everything. And I think as we'll see, I think I've got a note on this. Yeah, we found this out last year. There were a few mysterious things we couldn't quite resolve, and we realized that things that are on the stack are not going to be cleaned up when you exit. You're not going to see any destructors called. Usually the operating system will clean up any memory leaks on your behalf. But if you're really trying to understand how the system works, you might have been mystified to see that the stuff that's on the heap is actually going to get its destructor call, but not the stuff that's on the stack. So that's the only real caveat with the exit. And normally you don't want to have an exit somewhere in your code. You really want to handle things as gracefully as you can. Usually an exit is really an absolute worst case scenario. And so if you're dealing in any kind of a large software development effort, you're going to avoid that at all costs. And some development rules forbid the use of the exit for that reason. Absolutely, under no circumstances do they want to see somebody exiting it out of a very large program like that. So CERR is just like cout. You can think of it as a print statement, but it can be kind of separated from all of your other cout output. And a lot of systems are like this. You might not realize it, but many systems and platforms have a very more formalized debug or error output pipeline, if you will, and that's what CERR is for us. So we could just be doing normal couts, and at some point, detect an error and decide that we want to actually put this out in a way where it can actually be captured and sorted out of all the other stuff that you might be printing out to the console, which could be quite voluminous. And the other nice thing about CERR is you can redirect your output. If you're doing any kind of a runtime thing from Linux or the command line, if this was your executable a.out or whatever your executable name is, and you follow the name of that with &greater, you can redirect just the CERR information to some text log file, which is really handy sometimes if you're monitoring a very long and large process. Quite often log files are collected like this so that you can kind of look at them even while a.out is still running. You could kind of open the myerrors.txt file and observe later on kind of what got written out to it. So that's a nice tool to have when you're trying to organize all your output. Okay. Any questions on those two? Pretty straightforward. Just wanted to make sure that everybody knew the details there. Okay, good. All right, well, let's talk about assert. So assert is an interesting animal. It allows us to verify some true fact at runtime. It's kind of the equivalent of checking to make sure gravity is still there. You kind of figure out something that should absolutely be true, and then we put an assert in our code to test the truthness of that. And if that truthness fails, then we know something has gone horribly wrong. So we might say something like that: assert false equal true, right? So that, of course, is going to exit the program, because false is never going to be equal to true. And if that fails, then we're going to exit the program with an assert. And we'll see a little bit of information that the assert occurred and maybe what line it happened on. But without a little trickery on the side, we may not even really understand clearly who threw the assert or why it's there or what the reason was. So, but that's essentially what it is. And usually people get this, if they're going to get something wrong about this, they get it flipped. They'll think we're asserting a false statement, and that will cause us to fail the program. But we're really just assessing whether something that should be true continues to be true with that assert. Okay. Any questions on that? I mean, we'll elaborate on that and do some exercises. Okay, let's push on then. And like I said, I'll repost the links before we get to our first exercise here in just a second. Oh yeah, here's a nice handy thing we'll do. So this is a little trickery. So you can say assert false equal true. So there, we're obviously, we know that fact is not going to be true ever. And then we can put a double and on there, create a conditional, and just put in a character string that provides us with a little context, so that when this assert is tripped, which it would be in this case, we'll see a little bit more information about maybe where this happened, but it's up to us to kind of put that message in there. So that's something that is unofficial. Folks have been doing that for a while with this traditional assert. I don't know if I mentioned it, but we have to load the cassert library in order to actually use those things. So there's an example if you want to click into it at any time and see. I'll put up the links in just a second so you guys can click into that as well. So here's another example. Actually, why don't I do that now, because I think we've got probably mostly everybody we're going to get today. So hold on, let me just repost the links file for those of you who missed it the first time. I'm having to scroll farther and farther these days to get to the bottom of the list. File. There we go. Okay. All right. So yeah, so here's how you might typically use an assert. You know, we of course everybody should remember we can define these preprocessor variables. So I'll define a debug there. These are the same kinds of things we would use when we do the inclusion handler strategy that we've used so many times. But here we can say if debug, and then we can surround our asserts with an if debug and if. And what that allows us to do is put asserts all over our code if we want to, and then with one compile time change or one of these, debug changes, we can undefine that debug, and all that code will get stripped out, right? So we can do that. You can think of it as scaffolding. It's kind of something you put into your code to actually help you test stuff while you're just in the beginning phases, or maybe we're looking for a really nasty bug. Maybe as part of your new job, you were told, hey, we're crashing when this user data file gets loaded. Figure out, why we're crashing. And you could go through and put in a bunch of asserts if you wanted to, but you might do that inside of these if and def or if-def debug statements so that you're not slowing down the runtime execution of the program, because these things do have a little bit of a cost associated with them, right? So let's try a very, very simple example. And these are runtime asserts. So I have this function. We're going to keep coming back to this over the course of the lecture. It's a little bit of a bit to learn the first time out of the gates here, but you'll see it a couple times today. So we're trying to just calculate the sum of squares of two vectors. So we have vector of ints A and a vector of ints B, and we kind of want to just multiply the corresponding elements by each other and sum them up. But what do we do if they're not the same size? Well, we're going to pretend that's a big problem. We could probably find a way around it, but we're going to use the assert to verify at the runtime that these things are the right size. They're the same size, that is. And then we'll put in a little extra message to give some context to that, and then add this debug framework around that, and then give your program a test. So that's what we want to do. So if you want to click into that, we'll take a couple minutes on that just to give you a chance to get to know this sum of squares function also, and to implement your assert. So give that a try. I'll just kind of narrate over the top of that if I see any interesting problems as I'm looking again at the source code. Okay. So I'll give you a couple minutes on that. So I'll describe the template again for the folks who may be a little rusty on that, but remember that what we're doing here is our sum of products. It takes some type T, and that defines what our vectors are going to be: int, float, double, string, and then it returns that type T as well, right? So it's just returning a copy of, or an actual integer, right, or a float rather. Okay. And it's kind of meaningless what we're returning, to be honest with you, but I'm sorry, I take that back. It's not meaningless. It's the sum of the products that we're returning. Sorry, just thinking we were in a different function there. And if you want to just do your assert first and come back to your if def debug, that's of course fine. Remember, if you want to put a message in there with the double ampersand, it'll give you some ability to annotate your assert when it actually fails. So if you do that and you get that running, you'll see, of course, you can tell from main that these two vectors A and B don't have the same number of members. So when we get inside of the sum of products function, we're going to want to test for that right away before we obviously go into our for loop there, because otherwise we might overreach in one of those vectors. So we can say assert a.size equal b.size ampersand, hey, there's a bug in some of products, the vectors don't have the same size, something like that, right? So that's pretty straightforward. The ampersand message is really helpful, good to do. Remember, we're testing truthiness or truthiness. We're not testing that the two things are not equal. We're testing if they are equal. We're trying to assert a truth. So that's something that tends to get flipped around, and probably, you know, you would see a test for that on the quizzes and the final exam as well. So just make sure you're clear on that idea. It's pretty straightforward. Any questions on the assert? Okay, cool. So let me see if there's any key points here. Yeah, there's a little bit performance cost. So we tend to pull it out, or at least have this kind of pre-compiler wrapper around it so we can effectively have that stuff stripped out automatically. But it does tend to really kind of muddy up your code if you throw them all over the place. So often you'd see something put in like that when somebody's debugging a real nasty problem in some version of a software that you're trying to put an update out for. So you kind of build some asserts in there and dig in and figure out what it is, and then clean that up before you put it back out. You would, of course, never want to leave in there, because you know you're going to have, these tend to be in highly performant software packages, so you don't want to be running asserts all the time. And you also don't want to have any kind of messages like, uh-oh, if this happens, we're really screwed or we're hosed. I actually work with folks who have done that before, and it did not go down very well with management. So it's always better to wrap your stuff in a compiler preprocessor like that, preprocessor statement, so that you can have it stripped out. So that was a runtime assert. So that's been around for a while. So I think in C++11, and that runtime assert requires the C assert library be loaded. Static asserts are a little different. It's a compile time assert. And these are maybe a little less common, but they're nice to be able to do at compile time. And of course, because of that, they don't cost us any runtime problems, but they ensure that while we're building the software, nothing sneaks by us, right? So we can test a few things that are constants, that are easy to test at compile time. And then if that fails, just like with the regular assert, then we can get a message. Now, in this case, the syntax with static assert is a little different. It's got a formalized second parameter that allows us to put a message in to explain what that static assert was. So very, very similar to the assert, just at compile time, okay? Yeah, let's see, any key items there? Not really. Right, yeah, that's right. Because it's compile time, we can put it really anywhere, right? It can be outside of main or outside of a function. It's easy to test. So here's another one that might be common. A lot of times libraries get built for different architectures. So people are building large software systems that they intend to port to different devices. OpenGL is a graphics library that I think I've mentioned before. There are many others that you can imagine if it's running on a mobile phone, if it's running on an embedded device, or it's running on you know, a Macintosh versus a Windows machine. All of those, you know, there may be a lot of values that are quite different. And so if the library thinks it's been compiled for Apple, but it finds that a particular register is not the right size, you would want to have some kind of assert. And you can do that during the compilation phase, right? So you can test the size of a particular integer or a double to make sure that it's the right size for what the software expects in that situation. So that's another common use of the static assert, okay? So any questions on static assert or assert? Everybody good with that? Okay, very good. All right, well, let's talk about the bigger topic of the day, which are exceptions. Throw, try, and catch. So this is actually a pretty universal concept that exists pretty similarly across many, many languages. I've seen it used and abused in many, many ways. For a lot of early developers in certain languages, it's a way to just write really bad code that will never crash because you can always catch it, right? So if you don't understand the code that you're using, you copy it and paste it from somewhere. The idea was you put it inside of a try block, and then you catch it. It's not a good way to write code. Really, it's better to write the best code you can, of course, and then use this system in situations where it's incredibly important that you don't crash ever, right? So these are, uptime critical systems where you have to catch some unintended situation and handle it gracefully, and you don't have the opportunity to maybe stop and ask the user to input some data again, right? So it allows you to handle these errors and to do it outside of the normal program flow, as we'll see. I mean, we can all write if A is less than something, then ask the user for more input or tell them they got to enter another number. But in a large scale system, we don't always have that opportunity. And so the handling of errors can get very complicated. And that's where exceptions come in. And especially in the case of libraries, right? I think we mentioned this once before, but if you were developing a class for, let's say, dealing with matrix math, you're multiplying matrices or multiplying vectors in matrices or doing some statistical analysis, and somebody gives you bad data, well, what do? You're a library. You have no idea the context in which you're running. And so you want to have a way to gracefully pass the status or the condition of error up the chain, the calling chain of functions, so that at some level in the unwinding, the appropriate library that called you or the user that called your function can handle it in the way that they see fit. That's the real critical thing about exceptions. We could all write if then else code, but it's really tricky to do that in a situation where you're 8 levels deep in a function call, right? It also allows us to move our error handling code out of the middle of our regular execution code. You can imagine if we tested for every possible error condition and had all the if then else stuff all the time, we start bulking up the code that maybe just doing the algorithm that we're just trying to represent in a really clean way. And so as we'll see, we can put the exception handling part separately away from the typical stuff that happens most of the time. And that handling part is called the catching, as we'll see. We can throw or raise an exception and then catch it later and deal with it somewhere else in the code, okay? So this analogy of throwing and catching is actually a pretty good one. We tend to throw a particular kind of piece of data that gives us some hint or contextual information about what error happened. And then our catcher catches that type of data and takes that data and uses it to explain maybe to the user or to recover in some managed way or to gracefully shut down, right? So it cleans up our code, it keeps some of this error handling, and the stuff that doesn't happen that often, but when it does, you got to have a really comprehensive way of handling it. It gets that code out of our way and puts it in the catch section rather than where we actually detect the error, okay? So here's some simple examples, right? So we have a main program, we have a null pointer, and if we detect that we have a null pointer, we can just say throw, and we're going to throw a character string. Now in this case, we're throwing a message that says oops null pointer, but because you can see here, there's no catcher for that throw. There's nobody here that's catching a pointer to a string or a const char. And so what will happen, you can always throw an exception, but it ends up being essentially very similar to an exit. If there's no catch to catch the throw, then we leave the program almost always. So that's lesson number 1. It's going to essentially exit if we don't have a catcher. And the catcher, as we'll see, has to match the type of the throw. Here we're throwing a string, we have to have a catcher for the string, right? So we're going to need to learn how to add a catcher, okay? So let's look a little deeper at that. So we throw some value, right? This is our exception, or we're raising an exception, or we're throwing an exception. And it's a bit like a function call. We're passing that value through the throw to a corresponding catch. what's weird and different than we've ever seen before is the throw and the catch. The throw is the function call, and the catch is kind of the receiving part of that function call. And this value gets passed between the two. It's probably the most confusing part. But the reason we do it is because these things exist in very separate locations in our code. So we can have a try block where we say, hey, we're going to try a bunch of things here. And maybe if some bad conditions happen in one way, we're going to throw some A value. And if they happen in a different way, we're going to throw some B value. And these might be of different types. One could be a float, one could be a double. And as weird as that sounds, we're going to have catchers based on the type that's thrown, not on the value of that. So if this is a value of 1, because it's an integer, and this is a value of 1.0 because it's a double, those are going to have 2 different catchers, right, to be caught. And if there are no catchers, like I said, it'll exit the program, okay? And we'll look at how all that structure works. So when we leave the try block, right, whenever we throw something, we leave the try block immediately, and we immediately go to look for a catcher in some other block, and we'll look at that code. And that's basically what happens. After the try block, there's usually a catch of a particular type and its associated error handling block as well. And we can have lots of catchers. Like we could have a catcher for type A and a catcher for type B based on what kind of error was thrown. It's a little weird, and we'll explain to you kind of why it's done based on type and how you can, craft that to do something more meaningful for you. But that's the basic structure. We try. The try sets the scope in which we're going to try any number of things. And if there's any kind of exception raised inside of that, we immediately look for the nearest catch scope that allows us to deal with a type if we find a match. And we can have a whole bunch of catches that go with that try because we could have many throws that come inside of that try. Okay, very, very unusual. There's no other syntax really in C++, but this syntax sort of transcends languages, and so you can't too much blame C++ for it. So there's our try, there's our catch for int, there's our catch for char. And notice that here I have a catch int I. This means that that I is available to any code logic that we implement inside of the catch, right? So let's say I throw an integer of 1, and I might, in my catch block, I might know that I could have a switch statement for various integers to say, oh, okay, well, depending on the value of I, I'll know maybe something about what kind of error was actually thrown. So in addition to it getting an int, we can actually name what the int is and make use of it. If we don't care what it is, we could just, name the type and know, well, somebody just threw a character, raised a character exception. I know that that means I got to exit. Like that's just the way maybe the code was written. That by design, it was agreed that anytime anybody throws a character, we're going to do a very specific thing, right? So the catch is based on type, and we have the additional opportunity of passing the value that's thrown into there. I mean, we're always going to throw the value, but whether or not we actually utilize it depends on whether we give it a name inside of that, that set of parentheses there, okay? Any questions on that? Okay, and the key bit here that I probably did not emphasize enough is that in the spirit of exceptions, we really don't want to leave the program. We really don't want to have to leave the program. We want to try to take the execution to some other place so we can clean stuff up and then maybe continue in a different way. So what happens is as soon as we have a catch that matches, we continue at the next line of code that follows this list of catch blocks down here. So if I throw 1, I get a catch here in the orange, and the next thing I do is I print continuing. And so you'll definitely see some questions on the practice quiz and the practice final that will test your understanding of where execution continues after a particular exception is raised, whether it's a character or an integer or a double, okay? All right, so that's key. We're trying to continue. That's what we're trying to do with these exception handlers, okay? So we don't have to blow up and leave the program, because we could always just throw an exit in if we wanted to quit the program, of course, right? So there's where we jump to our corresponding type, right? Or we go there for that purple one for the character. Okay. All right, and so here's another way of just thinking about it. If I have a bunch of stuff inside of a try block, and I, throw these to my catchers, right? It really doesn't matter what order they're in. If they're all different types, the appropriate typed one will get caught, right? So if I throw a character, it's going to go to the character catcher if it follows this try block, right? And then, as I think I mentioned, if there's no double and I throw a double, then we're gonna terminate the program, which would be a bad thing, right? You might think you have a catcher for a double and you don't, and now the program's dead. So, so there always has to be a catcher so that we can continue execution. That's the key bit. Okay. So we're gonna try this. We're gonna do two of these. I call them 2A and 2B. I think the first one is just a continuation of our sum of products. So we did an assert last time when the sizes weren't the same. Now what we want to do is throw an exception and then catch that exception in a nearby catch block, so that we can just report that, hey, these two sizes are different. I can't do anything, right? So we want to implement a try block around the outside of the section where we are going to check the size. And if we find that the size is different, then we're going to throw an exception and we're going to pass the smaller vector. So we're actually not going to pass an integer here. We're actually going to pass a vector of type t, because remember, this is a templated function. So we're going to throw a pretty sophisticated thing, which is essentially a container. Okay. And then in your catch block, you just want to print out an explanation that says, hey, this little vector here isn't big enough, right? So we're just getting the smaller of the two vectors, and we're going to use that past vector to be able to report on its size, which is one of its memories, as everyone should remember, okay? And then it's just a question, does your catch block terminate program execution? You should know the answer to that, but you can try it out and find out, okay? So give that a try, and I will narrate, and let me know if you have any questions. Okay, we'll take about 2 minutes on that.
Professor, I have a question.
Yes.
Wait, I'm just catching up here. When do we catch it? Like, when do we need to catch these errors?
So if the goal is to not crash your program, then you want to catch them always. And so many errors, to be honest, the kind of errors we're dealing with today, we could probably deal with it if then else. And our practice 2B will show the conversion of a pretty easy to handle error over to a try catch. But the when is kind of whenever you throw it, So if the size of the two vectors, in this case, it's a little contrived, but we're just saying, hey, in my sum of products function, if sum of products of if a dot size size is not equal to b dot size, then we can't multiply the individual members together. So we're going to raise an exception right then and there. And so that all has to be inside of a try block. And I'll wind backwards so we can look at that try block.
I see. But if that case, why isn't it just all one statement? Why does it have to be throw and then catch?
Yeah, I know. Yeah. Well, so
they're going to be right after one another. Why wouldn't they?
Well, we're kind of working our way. That's a great question. We're working our way to the real unwinding potential of this try catch. We're going to see in about 2 exercises here that the try and catch don't need to be anywhere near each other. They could be in separate files, which is a little mind-blowing, and they can actually be hierarchical as well. So what we'll see is that the catch tends to not be near the try necessarily. We're starting out really simple, and yeah, and when you look at it, you're like, boy, that's a lot of code, and it looks really weird. It's not very C-like. Why don't we just do an if-then-else check? But what we'll see is when we look at a constructor and failure in a constructor, some of you might remember this, it's like, oh, I can't return an error condition in a constructor. I can't return anything because a constructor only returns an instance. So what do? Well, the answer is going to be exception handling. So we can try inside of our constructor and then throw some exception that will be caught somewhere else, not in our constructor.
Yeah. Wait, but aren't throws? I'm looking at a simple throw, and throws only come out of conditional statements. So
Um,
how does try work if throws are inside it? You can't have an if inside the. Can you have an if inside the try?
Oh yeah, absolutely. Yes. Yeah. So the screen we're looking on right now, you can say if, A dot size is not equal to B dot size, throw uh, B, like whichever one's smaller, you throw that vector, or you could throw a message, or you could throw a character. But yeah, it's totally fine to have these conditionals in here. It's weird this the structure is strange. Try braces is kind of a weird animal. It's not a function really. It's just scope, but it's a scope that tells the runtime, hey, please remember that if you get any kind of a throw in here, just exit that and start looking for a try as soon as you can, right outside of the scope, right?
All right. I think I
Yeah.
see.
Because nothing, and maybe I didn't say this either, it is leaving immediately on the throw. It is not going to stick around to check any other error condition. If you throw a 1 here, it's out of there. It leaves that whole try block. So if we didn't have the try block, it wouldn't know how far to go to start searching for the catch, kind of. Although I think you and everybody else and me too could come up with better syntax than this, but this is kind of the universal syntax that exists across many, many languages.
The try is actually a prompt for when throws are thrown to look for catches all throughout the code in the
Yes,
program.
yes. Yeah, it's a scope. We're specifying a scope that surrounds, all potential errors that we could, yield, or exceptions that we could yield in a particular area, like a constructor or a
Yeah.
particular portion of a function.
Let's see.
Okay. So yeah, let's take a look. Not to rush anybody too much, but let me see if I can get us back there. I don't. Some of these I didn't list the code, so don't feel rushed too much. I just want to see if there are any key bits. Probably more just observations. Maybe I'll switch over so you can see this stuff. The key things here before I do that is just to identify again. We're only throwing one thing, and it seems very limiting. It's like, well, what's the point of just throwing the smaller of the two vectors? What if I wanted to know which two vectors caused this to happen? Or let's say I was processing instances of a person class, and one of them had corrupted data, and I kind of want to know all about the person class, right? So it seems limiting to only be able to throw one thing, but as we're going to see pretty quickly, that will devolve into, okay, well, we're just going to throw instances of classes because it's a nice package that contains a whole lot of information that gives us information about the particular error.
See, and then just one last question. You were saying it's a scope, try is a scope.
Mm-hmm.
Do the throws look immediately outside the brackets of try, and that's it?
Yes, they do. And it's weird
Oh,
that it's weird that catch kind of is floating loosely there below try. It's like you could put extra code in between the try and the catch and see if you could fool the compiler. It's a weird syntax, if you ask me. It's not very clean, but it's just what everybody does. It takes a little getting used to. So yeah, any other questions on that? I will see some more examples of that. Maybe I won't dig into the code on this particular one because you're going to see a bunch of this stuff. I will do this on the next one, I think, because it's probably a little more elaborate.
yeah. And the catches have to be inside that external scope to work at all.
Yes. You can't put the catches inside of the try unless they're nested catches. I hate to qualify everything, but
Yeah.
we'll get there in just a second, and I'll show you that. Let me see if I can bring this up so you can see the code. I do think it's probably important. Let me see if I can switch over my share here. You share. So hard to know which one I'm actually choosing. Okay. Are you guys seeing my replit now? Is that coming through for anybody? Give me a thumbs up, maybe.
Yeah.
Okay, got it. Thank you. Okay, cool. Right. So here I'll just scroll so you can see. So yeah. Here's my function. Oh, this is the assert. Let me just kind of click forward. So that was a reference thing. Right there's the practice, and I think that's the solution. Okay. So try to catch. Is that? There's the solution. All right. So takes replit lately has been a little bit. There we go. Okay. So here's my try block. I'm going to say try if A of size is less than B of size, then throw A. Otherwise, if B of size is less than A of size, throw B. So we're throwing the smaller vector to the catcher, right? And then the catch is right there outside of the try scope, right? And it's going to, do something, right? And in this case, we're just going to return right away, right? We're going to say, hey, I can't do this. These things are bad. I'm going to send back some temp value of 0, but I'm telling you right now, like something bad really happened. So I'm returning. Otherwise, I go ahead and do what the function was intended to do. That's just one way we could try catch. Now we could have done that without the try catch in this case. We could have just done just a simple if then else, but we're kind of just getting ourselves used to this try catch structure. We'll see the greater potential of it here in a little bit. Okay. So let me switch then back to, there it is. Okay. PowerPoint. It's like jumping from tall branches on high trees. I never know whether everything's going to work when I switch over. Okay, so that's our try catch first example. So let's do another one. So we're going to try to convert from a standard if then else logic to a try catch. So it's pretty similar game, slightly different situation. So just this is having you kind of write this again more from scratch. Put the try block around your if then else logic, and then throw an error, right? If something bad happens. I think in this case we're trying to test for a divide by almost 0, and then we're going to try to catch that and handle the error in some way. And so you really just can mirror the logic that's already there, but we're going to move it into a try catch kind of representation. So give that a look and ask me questions, and I'll look at the code here as well so we can talk over that a little bit. Okay. Set the timer. So the idea of this function or this program that you're looking at is just, it happens a lot actually, especially when you're doing a lot of math. You get some number, it's not 0, but it's pretty darn close to 0. And you're going to be returning garbage, right? And so you really maybe want to warn somebody about it, or maybe you want to change the value of the divisor. So we have a numerator and a divisor here. Maybe you'd want to do something like, oh, I really never want it to be 0 because that's just going to create junk. So I'll clip it at 0.1 instead of 0.0001, let's say, for example. So the goal here, again, is just restructure that into a try catch. So we'll be raising the throw or throwing from where we have the oops there. That would be the equivalent of our throw. Okay. So give that a thought. Okay. Okay, so I may try this. Feeling lucky, so I might try this. Oh, I have it here. Okay, good. Hold on one sec. So let's take a look then at the solution for the code. So we have our numerator, divisor, or numerator, denominator, and then, assuming the user is going to enter those two values, we'll try to see if we can do a divide, right? So we say if b is less than 0.1, oops, that's just too small. So we're going to throw an exception or raise an exception. We're going to throw b because we're thinking, well, maybe the catcher wants to print out that value just to let the user know, hey, that was just too darn small, right? If we don't throw, then we're just going to do the division like normal. We're going to assume that we won't have junk as a result. And then here's our catch, right? So as you were saying, or was being discussed, catch, we're going to catch a double. So we have to have type, and we can optionally name the variable that we're receiving or the value that we're receiving, right? So notice I've named it something different. It doesn't matter what we name it. It's like any function. We're receiving something passed in as an argument. And now we can, process that, write something about it by referencing that value, okay? And as the point was made, it's kind of like, man, it's like right there. Why couldn't we just do it the way the code was originally written? And we can, and this is probably not the exact kind of error you would necessarily in this situation, raise an exception over. You could find maybe a more elegant way to do it because we have a user there that we can just prompt, right? But this is the equivalent structure to what we're seeing, before you had to convert this, okay? So the before after may be a little helpful, okay? So that's kind of the first approach to that, where stuff's pretty simple. So now we're going to look at nested try catch, and this is really where this unwinding thing is what exceptions are all about, right? So we can do some pretty crazy things to get our catch blocks very far away from our try, especially if we have a lot of code, or if we don't know how the user wants us to handle an error. The user gives us bad data. We're the library writers. We write the library, and we just don't know what, do they want us to, give them back junk, or do they want us to, abort, or what do they want us to do? So we can let them do the catch and not us. And that's the whole point for deferring the catch to somewhere else, is let somebody else decide how they want to deal with this error. I have no idea how you want to deal with it in your particular case. I'm just writing a library, right? So it's probably going to be somewhere else altogether, potentially outside of the function. So here's an example of that. So we have a try, and well, we'll do a nested try to start. So we can try at multiple levels that might occur, in multiple areas in different functions, right? So we have a throw, 1, 2, 3, 4. And the first thing we're going to do is try to catch that at the try that we're inside of. We're going to look for a catch there, and we have one, but it's not the right type. So what's going to happen? Well, since we're inside of a nested try that maybe was set up in main, or it was set up maybe in our current scope, typically it would be in another function call. We would then fall back to the catchers for that try. And here we find a matching type, and so we'll actually handle the throw at that point. And I know this seems really weird. It's like, who would write code like this? But as we're going to see, that what we're going to be throwing are really going to be instances of classes. And so what we're catching against is going to be a divide by zero error instance, or a bad argument instance, or instances of classes that were specifically created to deal with certain categories of errors, not just throwing simple data types. So we're using these simple data types to keep things somewhat straightforward for us. But this kind of a system is what's going on all the time. And the tries, as we will see, can happen in main. You could have try, call my function, and then inside of your function, that function might have another try, and then that function may call another function that has another try. And so when they unwind, this structure of effective nesting it sets the control on how we actually search for the catches. And that's why the catch is somewhat, loosely attached to the try. It can be somewhere else altogether.
Oh, so they don't come in immediate pairs?
No, not necessarily. I mean, if there's no catch here, then it could be somewhere else. I think we'll try to do them all together, but because of this nesting of tries, the catch that you eventually fall to might be somewhere else entirely and not one that you yourself have set up. You
Isn't
could
that
have
kind of like, yeah, oh, sorry.
go ahead, go ahead.
Isn't that kind of like spaghetti programming though? How do you keep track of all these?
Yeah, it's not. I don't love. You can guess why I save this to the end of the semester, because if we run out of time, I don't have to teach it. I'm being somewhat facetious, but you can get by for a very long time, in your career without going big for try catch, right? Um, and like I said in the beginning, like there are people, well-meaning, but write some very bad code because they figure, well, I'll just try, and if it crashes, I'll catch it, and I'll just print a message or something, and that's not the intention for try catch. But yeah, it is. It's a problem. It's a solution to a problem that you admittedly wouldn't get to in your careers until you're working in a much larger software framework with a lot of formalized, probably senior architects saying, hey, we are going to catch errors in the following way.
Yeah,
And
well,
usually
yeah.
that's when it's a third-party library. Go ahead.
Oh, I see. And where is this catch? Where's this catch cars? Character C. Where's it like relevant? Like, where's the first half of that?
Oh, well, so there's no throw that matches that catch
Yeah.
inside of this try. So it's kind of silly to have a catch there, right? To some degree, I put it there to demonstrate the failover into this other catch. But yeah, you would probably never, if you had no throw in there that was relevant for that catch C, you wouldn't have a catch C there. It would just be silly to have it.
So
So
then, what's the point of this nested stuff? I'm sorry, I don't get it yet.
hopefully the next exercise will bring it a little more into focus. The analogy is when you're in main and you try to create an instance of a class, right? And you give it a bad value for its constructor, and the constructor has to fail. The constructor wants to raise an exception. It wants to try and then throw an exception, but it wants you in main to catch that exception. It doesn't want to catch the exception because it doesn't know what to do with it. So it's going to raise it, but you need to have your try block around your attempt to create the instance in the first place. So we'll see that in just a second. It may take us a few exercises to get there, but I can relate to the confusion or just the like, this seems terrible. It is a little bizarre. I totally agree.
Yeah.
So there's our kind of theoretical nested try catch. So again, you raise it here, but it's an int type, and it's going to fail there. And if we didn't have an outer try block, we would crash the program, right? The program would just die because it's like nobody caught the integer. But here is a nested one that may exist in some outer scope, as we'll see, and it knows what to do with that. It's going to print.
Does catch always have to be inside try?
No, but a throw has to be inside of a try if you're going to catch it. You cannot catch a throw unless it's inside of a try, right? So that's the key point. There's a try block and a catch block, and the throw that it happens here can only be caught by a catch that follows the try block that it's currently in. You can't just say throw and then catch. I'm pretty sure that's not going to work. It's got to be inside of a try block. Okay. Strange, I know. Let me press on and see if we can get to more clarity. So here we're going to, once again, we're going to look at our sum of products. We're going to put the try around the call to sum of products. We're going to push the raising of the exception. We're going to leave it in the sum of products function, but we're going to wrap the try around the actual function call to sum of products, right, in main. And so we're not going to leave the try block in the sum of products. We're going to move it into main, and we're going to leave the throw in sum of products. And then we'll have our catch. So we'll still have our try and catch together, but now they're going to be in main, okay, just to exercise this distancing of where the throw is. And it might seem like the throw is not inside of a try, but it is, right? That's what our goal is. We're actually going to have the try wrapped around the call to sum of products. And the throw is still inside of a try block. It's just happening in a deferred way because it's inside of the sum of products that we're going to call, okay? take a look at that. I realize it's sort of getting more complicated, but you're seeing, let me make sure I have you guys on the right share, right? You're not still seeing the, yeah, you're seeing the PowerPoints. Yeah. So take a look at that. Maybe I'll switch you over to the Replit here so that you can see the code for a minute, and we can talk about that briefly, and then I'll let you guys take a crack at it. So this is, this was our previous one. So that was 2B. So now we're on 3. Yeah, 3. So this is what we're working on here, right? So we've got this sum of products function, which has a try catch inside of it, but we want to move that out here, right? We want to move the try to be around this function call here and then immediately catch right after that try. So all of that try and catch is here, but we want to leave the throw here inside of this. So we're going to remove all of this stuff and just leave the throw all by itself. We're just going to make sure that we wrap this call here in the try and catch. Okay, that's the goal. Oh, sorry, I missed that. I missed that question. You threw a void. Yeah, good. I love those. It is a type or a non-type, I guess. Set a little timer so I don't lose track of time. I talked a bit over that one, so we'll give it about another half a minute and then we'll.
What does try do again as a block? You said it's a scope, but in the solution, you're setting final sum inside it?
Yeah. So tries, like, think of tries like the safety. I don't know if you ever played bumper bowling. You know, it's kind of the boundaries around an area where something bad could happen, you know? So we say try, and then we use braces to set the boundary area of the danger zone. And in this case, we're setting that boundary area to be the calling of the sum of products function. We're saying, okay, something bad could happen in there. I don't know exactly what, because I didn't write that function, but I'm going to put a catcher here that's going to catch, you know, a couple different types of errors so that I can deal with them. So we're pretending we don't know what's going on inside of sum of products. It may throw some exceptions. So we're going to want to try to catch some potential exceptions that happen inside of that sum of products function. And I realize it's like, well, how would I know? But we'll talk kind of about how you'll know that in just a few minutes.
I see.
Okay, let's take a look. And while I'm here, I'll just, yeah, okay. Yeah. So we'll just slide on over to the solution here. I don't love looking at code this way because sometimes it's just hard to see. But so here's the difference, right? So we kind of simplified our function back to the kind of code that we would like to write. You know, we just want to focus on writing the function. But if, you know, one of these guys is the wrong size, I'm going to throw, basically, I'm going to throw a kind of an exception that is of type vector t, right? Because A is a vector t and B is a vector t. So I'm going to throw a vector t exception, which seems a little silly, but it at least allows me to pass along some information, let's say, about what that error was. But the scope is changed, right? So we put our try here around the function call up at the main level, and we have our catch right here. So we don't know, let's say, what's going to be thrown, but we're going to guess, you know, in this current simplified world, that it's going to be some vector of type int, because that's the kind of template type that I fed to the function in the first place. Okay.
Oh, so you can have a scope. That's what you mean by still having a scope, is that?
Yeah, exactly, exactly. And I could have multiple function calls in here, right? I could have try, maybe like there's sum of products and then there's, median. Maybe I call 8 different function calls from 8 different vendors, from 8 different libraries. And I'm thinking one of them's going to screw up, but I can't afford to crash my program. So I'm going to put a ton of catches here and try to catch, all of the different possible bad things that could happen. Now, I'll say bad things in air quotes because we'll talk about how we know, like, how do I know what kind of type is going to be thrown from inside of these functions? That's a
Yeah.
fair question that we'll talk about. Okay. So let me switch us back over to the, where's my, oh, right, new share, back over to the slides. Getting better at this. Okay, so that's our nested try catch, right? I think we talked about all this stuff there. Yeah. So, and it is possible to do a catch inside, and then if we don't catch our own stuff inside of the function, we think, okay, well, I hope maybe somebody does. There's a number of ways you can cascade this stuff outward. Catch-all is good to know about, but not one we're going to spend, I think, any practice time on. But if you catch dot, 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 you're basically catching everything of all types, of every instance type that anyone could ever send. So if you really, really don't want to exit the program, you could do a catch-all dot, dot, dot. But you would want to put that as your last catch, your outermost catch, because obviously if you put it as an inner catch, you're going to be bypassing maybe some really helpful information, because you can't really say much when you do a catch-all. You don't really receive any kind of information about something that you can take apart and print data about that particular throw, right? So I could throw some data type and then catch int, catch dot, dot, dot. So if it's not an int that gets caught, I can then do the dot, dot, dot and say, uh-oh, so, uncaught, or, random catch. Don't know what to do here. Please look more closely before you ship the code, kind of thing. Okay. So you always want to be careful with the order of that. So that's just an FYI catch-all. Okay. So let's see. Oh, this here's just that. Yeah, doesn't really add a whole lot of value, but we can do it. And of course, as we said, if you don't catch something, the program will terminate. Okay. So the whole point of this, where we're going then with all of this, is exception classes, right? So we can throw integers or we can throw characters, and that's okay. But if we really want to pass along a really comprehensive bunch of information that's going to survive intact, memory destruction and destructors being called, and a program basically progressively deleting or shutting things down, we really need to pass some instance of a class that carries data with it in a safe way, right? Because if you think about it, you could be inside of a constructor and you could leave that constructor, but you really need the piece of data that's thrown to survive. It needs to be preserved as a copy in some special part of memory so that it doesn't go away, because you want to be able to do something with that. So there are a lot of formalized classes that deal with exceptions. We're going to start by making our own first, so we know what that's like. But then we're going to go look at the standard library and see what kind of classes they recommend that we derive from. So the idea is just to create an exception class that we put special stuff in, like a message maybe, or maybe some special data that we're curious about, like what time did it happen? I'm just making that stuff up. You could put whatever you want as your members of your class in there that you want to pass along to your catcher. And so your catcher can name, ME stands for my exception here. It's an instance of my exception class. And now we can print out whatever we want to print out, member one, member two, some message, etc. So that's really what we're going to do. So here's an example of a kind of a simplified exception class. So in our case, we're pretending all we're dealing with is this vector function. So we have a vector t type T called A. So we've templatized our class, right? So A is a vector of type T. And then there's some message that we want to pass along that we can print out that explains what's going on. And our constructor, we need to construct our exception class here and set A equals to A, which is the vector that's passed in. And we want to set our private message equal to some const char string that's passed in. So we're basically building this little package of error information that's going to be chucked over to the catcher at some level in the program. So that's going to be our class. So what we're going to have you do is just kind of go in and tweak a few things on that so you can kind of see it. So we're going to use that as, you know, just a way to catch this exception information. And we want to have you give it two members, A and B, and we want to pass both vectors that are causing this problem in my sum of products function into this instance of my exception so the catcher can print out their respective sizes, okay? So we want to have, then you're going to need to update your constructor. And then when you throw the error, like we have been doing, just throw an instance of the class, which you can create as a transient class. You don't need to give it a name. You can just use the name my exception and then invoke the constructor and pass it in the vectors and the message, right? And then in main, we'll catch it like we were just doing, and then print out the size of the two vectors. And hopefully there's enough hints there in the code that'll help you out. I'll put up the structure of that. Or I'll switch over to the code so you can see that here in just a second. Is the goal kind of somewhat murky and clear? I'm trying to take us along a progression here so it's not too much all at once. All right, we'll give that a try. I'll switch us over so I can share the practice part of the code and field any questions you might have. So that's Replit. Go. Okay. Go. All right, so let me get us over to throw class. Right, okay. So here's our class. I gave you some hints on that, but basically we're just trying to create a templated vector of type T, right? So kind of asking you to remember your template type syntax, and then use your constructor initializer list here for your A and B, pretty straightforward there. And then throw an instance of the class down here. So you need to create an instance of the class that has the A and the B and some message of your choosing. Actually, do we have a message? Oh, we don't have a message, so don't worry about the message. Just want to throw vector A and B inside of that instance of the exception class. And then in main, we'll actually be able to print that thing out. So we'll say, oh, we just caught an instance of my exception of type int. The sizes are me.a and me.b. So like that. So give that a try. Okay, maybe another half a minute. Okay, let's slide on over to look at the code here. I'll just stay in Replit here for the moment. And let's take a look at Right. So here's pretty simple. We're just creating a class. We've done that before. It's vector t of a, vector t of b. We initialize with our constructor initializer list. So this is the creation of our descriptive exception, kind of for this specific problem. Would have been nice if we put a message in there too, but you can always come back and do that. But here, we're just throwing an exception of type T for A and B. And as you probably recall, without some reference, those things are going to be copied into there, right? So they're copied into the exception constructor. And then we can catch that outside in main here, right? And so that's an instance of that, which we know has an A member, which is a vector. It has size and a B member of size. So we're dealing with a richer set of information passed through that instance at some point outside of the function where the problem occurs, okay? And so this formalization, which there is a great deal of formalization of, hey, what's a great exception and what's a hierarchy of, or what's a family of different exceptions that are standard in the computing world that, you know, we can rely on and know they exist. So we don't have to go develop all of our own stuff, right? And so I think we'll see, I'll switch us back to our lecture notes so we can see that there is a pretty standard library for that, as you might expect. Let me just clear off my screen so I can see what I'm doing here. So there's just some takeaways, right? So we saw that in the code, right? And there is no magic about it. When I first started looking at exceptions, I found it very intimidating because there's this rich kaleidoscope of many different categorizations of different kinds of errors and these instances, and you have to look at the instances. And it was just very mystifying because it's like, what is all this stuff? You know, is it officially related to exceptions? Well, no, there's nothing specific about the class that comes from the standard library, except that, you know, it's like common rules of the road. So we can all start migrating in the same way. But the structure that we've talked about works if we create our own instance of a class. It's not a problem, right? But STD exception is where we would find that information, right? And the idea is that you derive from that exception class. And what that allows you to do then is go kind of try to catch more standard errors. So let's say you, in your, you just wanted to throw a divide by zero exception or a bad argument exception. We can find standard derivations of this base class that cover that case. And so we may not know exactly what's going on inside of the guts of a function, but we can expect that maybe it has some standard exceptions. In fact, quite often, if you read the documentation for a software library, it'll say, oh, well, I raised the following exceptions, right? So you can test for those exceptions in your catch block if they occur, right? So we'll look at that. We'll do a quick derivation, but let me go over to that page one more time. Sorry for all the jumping around, but I think this would be worth seeing just so you can understand. So I'm going to switch my share one more time over to standard exceptions. Here we go. Bring that back up. Okay, so you can kind of see, so this is, you know, the reference page for CPP reference. You know, and this is, you know, we have a base class exception, but then we have a bunch of other classes that derive from that in a hierarchy, right? And we all remember that, hopefully, from 2 weeks ago. So there are logic errors that, you know, have children, you know, derived classes, invalid argument, domain error, length error, etc. All of these categories have been thought about and formalized, and in theory cover, you know, a broad range of standard exceptions. And so the idea is we all, as writers of the function or as catchers of the exceptions, should be familiar with these so that we can write relatively standardized code. But it doesn't mean that you can't write your own exception. If you did, you would just try to derive from the base class so that, you know, we do it in a reasonably standard way. And if we were to look at the base class, we'd see that it's got a virtual member, right? Which means it'll be there. It's not pure virtual, so we can go there and see what the explanatory string is. But we can expect that if we click into, let's say, an invalid argument derivation of this exception class, you can see it derives from exception, logic error, invalid argument, and it's got its own explanatory string along with maybe some other stuff that it's going to put in here, right? So we're not going to dig into all of this, but I just did want you to know where to come, because if you ever deal with handling exceptions and it's done in a correct way in C++, you'll be coming to this page or something like this, so you can understand what kind of exception just got thrown, okay? So back in the PowerPoints then, let's just try a little derivation, sort of a sneaky way for me to get you to actually remember your inheritance code syntax. So the idea is we want to go right back into essentially what we had last time, but I've got a link here for you, and convert your, so you want to convert your class so it derives from std exception. It's very little syntax, but see if you guys can remember that. And then go to main and start out by trying to catch the base class. So you'll see that we can catch the base class always if everybody writes according to this base class. Even if you derive your my exception, you can still catch the base class. So we'll try that. And then we'll add a second catch to try to actually catch your particular derived class, your child class, which would be my exception, okay? So that's what we want to try to do, and then come back with some awareness about which one of these gets triggered and which one should go in what order in your catch, okay? So give that a try. That might be kind of winding down, so we'll be finishing here pretty quick. And I'll switch over to the code myself so I can look at some stuff here and see if I can highlight some things. So a key thing to remember about your derivation in your classes is that you want it to be derived publicly. And remember also that it's a different kind of public than the public members that we use there. And you will probably have to use std to do that derivation. Another half a minute or so. I think I'll switch this over to Replit again. Okay, let's take a look at that. So this was the before, if you will, there was our exception. And here's our exception with our magic little public derivation, right? We're deriving from the exception class. So that's going to be our base class. We're just adding our own members to whatever else it had, right? And we probably should have used its message rather than our message. We could have used the what message, but we chose to add our own. And then down below in our catch here, you can see now we can catch against our specific instance. Let's say we think, oh, I'm pretty sure sum of products is going to throw this derived my exceptions thing. But if that doesn't do it, then I'll certainly check the base class and see if that exception was thrown. At least I can catch it and do something. So you can imagine if you had a library, I don't know this in great detail, but I'll use the Havoc example. So there's a very, very large software library, cross-platform, and certainly they'd want to raise exceptions. And so there were probably, if they didn't, they would probably seriously consider if they could go back and do it over, have a derivation of a havoc exception class that derived from the standard exception base class, right? So you follow that best practice, right? So that's the idea. And, really you would very likely be just jumping right into instances rather than dealing with these individual raising of floats or ints or things like that. Okay. Any questions on that one?
So if you derive exception, if you derive your like how do I even say it? Exception goes down onto your new derived class.
Yes. Yes.
Then you can catch exception, and it catches everything that all the children of exception, grandchildren, all the
Yeah.
descendants.
Yeah. If you said STD exception here, I think you can probably see the PowerPoint slides now. That should be last, right? Because presumably you maybe tried some more specific stuff here with your derived base classes here. And if you didn't catch anything there, you'd want to maybe at least catch the base class exception. That you could do it that way, right? You could also say catch ... and then you'd catch everything as well. But you would want to start from specific and then go outward to general, basically. Yeah. And if you were working with multiple libraries, let's say, and they had all derived their own individual exception classes, you may have multiple catches here that are dealing with, OpenGL exceptions and then Havoc exceptions and maybe Microsoft library exceptions or whatever. But they would ideally all be derived from that base class.
So it's still good to have your instance in there.
Yeah, no, I think it is. Because if you think about it, you want to probably know and or say something about the error, right? So, and that error may be very specific to what you're doing with a matrix or some rigid body or maybe a very large data set. So although you don't want to really be passing around massive chunks of data, your particular exception may have some data that is useful to you, in handling that stuff.
Whereas having the STD exception there is just good form.
Yeah, it is. Yeah. Especially if you don't want to terminate the program, right? So I think we're going to look at one more, but I don't think we're going to do an exercise on it. So let me just do this because I know we're just winding down here, as we always do. Somehow magically at 7:10. I swear I don't practice that, but it just seems to happen. So we saw the multiple. Yeah, let's talk about the exception case, because I think this is one that, it's a problem that there's two kind of examples we'll talk about really quickly that bring it into focus. Maybe, well, what else could we do, right? Well, exceptions really are the best way to do that. So, and I think to do that, I'm going to probably just jump to the code real quick. So I'm going to go back to, bear with me, our Replit. Every time I do this, Replit jumps around. There it is. Okay. So let's go there. Let me switch over to that. This is okay. It's kind of messy, but it's surprising what happens here. So I've designed this class A. We'll start with class A. So class A has some member X, MX, and it also has a composed class B that lives inside of it. It's an instance of class B. I have my constructor, and then I have my destructor for A. And just for completeness, B is a super simple class up here. It's got a constructor and a destructor. So let's say something bad happens. I get a bad value of X that's less than 0. And and that value of X, let's say, is just not good, right? So I need to bail out of there. So I'm going to throw some exception. It doesn't really matter what exception I throw. But, it's interesting to see here the order of the unwinding, right? Because in main, I'm going to try to create an instance of A. And if not, I'm going to catch some exception. So I kept it simple and just used int, but it could have been a standard exception here just fine. And I might have said, "Oh, sorry, I couldn't create that instance for you. My bad. You gave me a bad number or whatever, right?" We don't really have that option here, right? We can print that message, of course, inside, But we can't really decide not to create it or to throw it away. You know, we've got a bad instance inside of this, right? And so this is a way of handling that from the outside. We might decide, okay, well, that lowercase a is just not usable, and I'm not going to continue. So I'll maybe reprompt the user, or I'll call some other function. It just gives us a means of managing the control flow of the problem out here, where here we have really no choice. We can't really pass any information out to the outside world that says, hey, you know, we can print a message, but that doesn't help us deal with the error in any controlled way. This lets us change the control flow of the function, you know, and there's really no other way to really do that. And while we're here, I think, just kind of maybe skipping over, no, I guess I don't have that. So we can do that to I think I only have slides for this last point, and then I'll wrap up and let you guys get out of here. So let me get back to my slides then. So the only other example, or another classic example here would be overloads for operators, right? So this would be a real nasty one to have to deal with. So when we overload a bracket operator, right, and we're making a class look like an array, you know, which we've seen done before in some classes, what are you going to do if somebody's using that bracket operator in line, right, in some long, you know, array assignment, right? You can't not execute that, right? So we need to stop control flow and move it to somewhere else and not crash the program, right? It's like, oh, you just tried to access an array out of index. I can't let you do that, because if I return a value, it's going to be a bogus value. So this allows me to change the control flow, to take the control flow away from the offending code and go deal with the catch somewhere else. That's the real key takeaway for exceptions. They let you move the control flow to somewhere else in situations where you really may not have had any other choice except to crash.
And let me guess, the catch is the try block is probably in main, right?
Yeah,
when this gets called.
Yes, yeah, it would certainly have to be, you know, in some way, I mean, in a reasonable way where you could express the catch in a reasonable place. It has to be inside of a try block in some place in order for you to catch it. Yeah, definitely. So just FYI, the Quizlet is up for this. If anybody wants to click into that and practice it, it's pretty painless, actually. There's a lot of true-false stuff, I think, that's pretty palatable for this particular lecture, and you'll see that in the practice quiz and the final. So hopefully that helps you with this particular lecture. And there's an audio, there's those typical audio explanations, which sometimes I forget. I thought I'd put a reminder up here. If you get a question wrong, you click on the kind of the audio piece over to the side there, and it'll give a little explanation if you were confused about it, right? And then next week we'll highlight some sections that'll be on the final. I think this is a little out of date. We're really going to go over also the factory pattern, which will be fun. We'll play around with the factory pattern just so you guys see what design patterns are. And then we'll do our formal real review on for the final on Thursday. But you will have a practice final exam and a practice quiz. I'm calling it quiz 7, but you'll have that as well at the beginning of next week, I'm pretty sure. Okay. And we'll go over all this next week. This is just some, if any of you were wanting to study over the weekend, you could go over your midterm, your quizzes, any of the purple slides, the Quizlet stuff. That's a good way to get started. But I will send you out more information on your study suggestions as we get closer. Okay, any other questions before I let you guys go?
Thanks so much, Professor.
All right, thanks everybody. Have a wonderful and safe weekend. I will talk to you on Tuesday. And don't forget your homework 9. Thanks. Bye.